This video is going to be a quick summary of two sections in the book, section 10.6 on quadric surfaces and cylinders, and section 11.1 on functions of several variables. The general theme of these two sections is more complicated surfaces. In the last section, we moved from lines to planes, which are two-dimensional surfaces that are flat and are characterized by a single normal that is the same everywhere on the plane. And so today's lecture summarizes these two chapters, which introduce us to more complicated kinds of surfaces that can be obtained by more complicated kinds of equations. All right, so in 10.6, we talk about things called cylinders and quadric surfaces, which are one way of creating a certain class of more complicated surfaces. And then in 11.1, we move to functions of several variables. In particular, we think about visualizing functions of several variables, which gives us another way to create more complicated surfaces that's a little bit different and has different limitations than quadric surfaces. So having said that, we'll go ahead and jump right in. The summary here is a little bit cursory in places. Where our main goal is to sort of get the idea. So although there are 7-8 pages of notes, this shouldn't be the longest of videos. So the first kind of surface that we'll consider are cylinders. And although the book gives a sort of technical definition of cylinders that's here at the bottom of this page of notes, basically in this class we'll restrict our attention to surfaces where one of the variables is missing. Okay, so the perfect example of this is a circular cylinder. Here we've got the equation x squared plus y squared equals 1. And of course that creates a circle in the xy plane if we're living in 2 dimensions. But if we're living in 3 dimensions, then z is not present in this equation and its value is not specified, and so z can be any value. All right, so here I've only plotted the values of z between -1 and 1, but really this equation describes a cylinder that goes infinitely high and infinitely low in the xyz coordinate space. All right, moving on, another variant of this would be, say, this image right here, which we could call an ellipsoidal cylinder. It's like a round cylinder, but it's not a circle, it's an ellipse. Here we have y over 2 squared plus z squared equals 1. Here it's x that's not specified, and so the cylinder extends infinitely far in the x direction from minus infinity to plus infinity. If we think about the shape of this cylinder compared to the equation, we can see that when y is 2 and z is 0, then the equation is satisfied. So we expect it to sort of go from -2 to 2 in the y direction, which we see here. That's the long distance of the cylinder. And when z is 1 and y is 0, the equation is satisfied. So it only goes to plus or minus 1 in the z direction. And so in general, this number underneath the y is the radius in the y direction, or the major axis. The larger number is called the major axis, and the number underneath the z here, it's just 1, would be the radius in the z direction. In this case, it's the smaller, and it would be called the minor axis of the cylinder. So these are both called cylinders: a circular cylinder, an ellipsoidal cylinder. The book takes a more general definition. So anything with a missing variable, it calls a cylinder. Here are 2 more examples. A parabolic cylinder, y equals x squared, very familiar shape from algebra and onward. So here's the y direction, and here's the x direction. The cylinder, the parabola opens in the y direction. Here z is not specified, and so we extend this parabola up and down in space to get what's called a parabolic cylinder. You can even have a hyperbolic cylinder. This is y squared minus x squared equals 1, traces out a hyperbola in the xy plane. Again, in this image, z is not specified, and so this shape is sort of translated through space in the z direction, tracing out this 2-sheeted surface as it goes. I do want to emphasize that although 3 of these examples have z as the missing variable, it doesn't have to be z. Here it was x, it could be y. In fact, the object could be projected in any direction. but the math gets kind of complicated in that case, so we'll just restrict ourselves to the x, y, and z directions. Right, so this just points out the book's definition. It's a curve translated in a single direction through space, tracing out a surface as it travels, but we'll consider a subset of those kinds of surfaces. Moving on kind of briefly, something called quadric surfaces. We already saw a few examples in the previous image, but a quadric surface is a set of points satisfying a quadratic equation involving squares, second powers of x, y, and z, products of x and y and z, x, y, and z themselves, and perhaps a constant. Okay, there's a ton of surfaces that can be described by these kinds of equations. We're just going to really briefly review some of the possibilities. This is not a heavy emphasis of the class, but I do want you to see the pictures. The most famous we've already sort of seen is a sphere. A sphere is a quadric surface. As we saw earlier, it's a set of points equidistant from some center point. It has this equation, as we've already seen, basically comes from this expression here. Magnitude of the distance between the points in the surface and some reference point is the radius r. And then you square that out and write it out longhand. You get the equation for a sphere. So here's an example. Sphere of radius 1 centered at the origin. You can modify that a little bit and get something called an ellipsoid. It looks very similar, except now you have numbers in the denominator underneath the x, y, and z. Basically, these are sort of the extent in x, the extent in y, the extent in z. You can call it the radius if you want. I'm not sure if that's standard usage. But here's an example. X over 3 squared, y over 2 squared, z over 1 squared. You can see that its longest distance is to plus or minus 3 in the x direction because of that 3 in the denominator. It goes to plus or minus 2 in the y direction because of that 2, and it only covers plus or minus 1 in the z direction because of that 1 there. And so you get this thing, it's called an ellipsoid. It looks like a squashed sphere or like a skipping stone, something like that. One of the more exotic shapes is called a hyperboloid. It's a shape that looks like a hyperbola when you view it from the side. These are hyperboloids arranged in the z direction. Sorry, they're not lined up here. But there's two kinds of hyperboloid. One is a hyperboloid of one sheet. We look at it from the side, and we see that it looks like a hyperbola this way, like a left and right facing hyperbola. This would be a hyperboloid of two sheets, and it looks like it's an up and down facing hyperboloid. Both of these have been then revolved around the z-axis because of my choice of orientation. Again, these are just kind of exotic shapes. We're not going to really focus on them, but you may see them in a homework problem or something, so it's worth putting up a picture. Finally, there's shapes called paraboloids. They look like parabolas when you view them from the side. You can have sort of simple parabola rotated around an axis. That would be, for example, this one, z equals x squared plus y squared. Looks like your standard parabola in the xy plane that has been rotated around the z-axis. On the other hand, this object right here, technically called a hyperbolic paraboloid, is quite interesting. If you look at y equals 0, you cover up the y squared, then you have z equals minus x squared. And so in the x direction, it looks like a parabola pointing downward, right? Like this in the x direction. But in the y direction, it looks like a parabola pointing upward because you have z equals y squared. So depending on which way you look at it, it looks like a parabola pointing up or a parabola pointing down. And so this is a really interesting shape that we'll talk more about. The technical name here, the informal name would be called a saddle point, because you can imagine that this looks sort of like a saddle that would go on a horse. Your legs go on either side pointing downward, and the things in front and back keep you from falling out of the saddle. So we'll see more about these paraboloids later on in 11.1, which is really just this lecture. So at the end of the video, we'll see more about these. And these actually come up quite frequently because, as you'll notice, they can be written in the form z equals a function of x and y. which makes a nice transition to the second half of this lecture, functions of several variables. All right, so that was all about geometry. And this ultimately, this section will ultimately involve a lot of images and geometry as well. We want to take just a moment to kind of step back and think in a little bit more general terms. We've been sort of hinting at this for some time now, but what we're really going to talk about in detail today are functions of several variables. So in Calculus 1 and Calculus 2, you were restricted to thinking about things in the form, say, y equals f of x, one variable functions. And now we're really going to put the multiple variables in multivariable calculus, and we're going to say, suppose we have functions of more than one variable, x and y, x, y, and z, for instance. Again, we have independent variables, coordinate variables, x and y. We have a dependent variable, which in this example I'm calling phi, and they have the functional relationship, f. So let's just spend some time talking about precisely what that means, a functional relationship between one dependent variable and multiple independent variables. Before that, let's talk about some examples. These are familiar to you from everyday life. You could think about a very common one that we'll use throughout this lecture for a visualization aid is to think of z as like an altitude that depends on local position, right? So like x could be east-west, y could be north-south, and f could be the function that gives you the altitude, z, as a function of your coordinates on the ground. Temperature. Temperature, in general, depends on altitude as well, but forget that for a moment. Let's just think about surface temperature. You could imagine living on the Earth, characterizing the Earth with a certain coordinate system called spherical coordinates, latitude, longitude, and you could think of having temperature be a function of latitude and longitude. That makes sense. We see maps like this every day. That's a multivariable function. In economics, you could talk about the price of an item and the quality of an item and the consequent demand for that kind of item. You can think about different relationships on price and quality, right? So in general, the lower the price, the higher the demand. But quality also plays a role. There are lots of cheap tablets available that are very low price, and yet demand may not be great for them because the quality is not high. Similarly, the iPad is ridiculously expensive, but somehow seems to be in high demand because it has a reputation for having high quality. And you could go even farther. You could talk about more than two variables. You could talk about lots of variables. Suppose you treat as independent variables the number of hours you spend studying for each of your class, T1, T2, T3, T4, T5, some of you T6, T7, and so on. What is your GPA as a function of the time you spend studying for each of those classes? These are all multivariable functions. All right, so technical definition of a function is that it's a mapping of members of the set of coordinate values to some value of the dependent variable phi. All right, so you've got x, y, say, two-dimensional space that's represented by this two-dimensional blob over here. And then f, phi, really, the dependent variable represented by this one-dimensional line, and f is a function that maps points in this space to positions on this line, right? So here's the point, x naught, y naught. Here's the mapping. It takes you to this thing right here, which we call, we could call that maybe phi naught is f of x naught, y naught. Here's the point x1, y1, maps to this point phi 1 that could be called f of x1, y1. All right, so this is pretty intuitive, but it's useful to sort of write it up formally. As in one dimension, the set of allowable values of the dependent variables is called the domain, and the set of all values attained by the independent variable is called the range. So same language and same meaning. We also want to be very careful and understand what we mean by like a limit, because all of calculus is based on limits, and continuity, because a lot of times we'll be primarily interested in continuous functions. So everybody loves when we pull out the epsilon and delta definition of a limit, but it's really not so bad. So the formal language is that we say that the limit, as the coordinates of the dependent variables r approach some specific value r naught, of the function f of x and y equals L. We say this is true if, for any epsilon, there exists a delta such that the magnitude of f of x, y minus L is less than epsilon whenever the magnitude of r minus r naught is less than delta. All right, this is formal language, and the first time you see this, it's just bewildering. It doesn't really make any sense. But there's a very straightforward analogy that you can use to understand what this means. All right, and it's very intuitive. And that's an analogy of archery. So suppose you have over here your point, x naught, y naught, which is abbreviated r naught. And think of it as a quiver, right? You're pulling arrows from this area, and you're shooting them at this target. So this limit definition basically says, no matter how small you make the target over here, right, for any epsilon, no matter how small, epsilon's positive, but it's small. No matter how small you make epsilon, I can make it this small, or whatever. No matter how small you make the target, I can still hit it. That means that magnitude of the function value minus L is less than epsilon, right? No matter how small you make this target, I can make sure that I hit that target somewhere in here if I draw my arrow from sufficiently close to the point r naught. And that's whenever r minus r naught is less than delta. Okay, so if this function has a limit, if the value of the function approaches L when xy approaches r naught, this process is true. No matter how small you make the target, I can always hit it if I'm sufficiently close to the point r naught. This is the formal definition of a limit. Okay, now in higher dimensions than 1, this actually gets kind of crazy, and you can have functions that look like the following. This is what we call a surface plot. Z equals a function of fy, x and y, and I've plotted it in what's called a surface plot of this particular function, and this function has no limit at the origin. Why is that? Because if I approach the origin from the y direction, here, the limit is +1. If I approach it from this direction, the limit is +1. This would be y equals 0, so I would cover up here, and I would cover up here, and you can clearly see that the limit is, no, this is x equals 0. I apologize. Along these lines, x equals 0, and you can clearly see that the limit is 1. In fact, the value is 1 everywhere along that line. However, if I approach from y equals 0 from the x direction, I cover up the y's, and you can clearly see that the value everywhere along those approach lines is -1. So approaching from one direction, I get 1. Approaching from opposite direction or perpendicular direction, I get -1. This function has no limit at the origin, even though it looks fairly well behaved. You've got this x squared plus y squared on the bottom, which is positive everywhere except 0, and that's why we run into a problem at the origin, because the limit is different from different directions, so it doesn't exist. Okay, that's it for formal discussion of two-variable functions. This is an applied math department, and we don't prove a lot of things. You might take a class called analysis if you thought the last 2 pages were really interesting. So now we're going to go back to visualization and two-variable functions as surfaces. And so the tool here is something called a surface plot. And this is something that like MATLAB or Python or Mathematica can generate for you. I've used Python here in these images. MATLAB is very approachable and is available free to students on campus. Python, of course, is available free to anyone in the world. So the idea is that you take every point x, y, you put it through the function f, and you get a value z, and that gives you a point in space, x, y, z. Right? Here is an example of a point. And here's another pair of values x and y that yield a different point, x, y, z, and so on. And you perhaps create a regular grid of points in the x and y directions. You get the associated values of z, and now you have all the points of these intersections, and you draw lines between them, and it traces out a mesh surface that we call a surface plot. And a lot of these software programs will, color them very nicely using, different sort of color maps. I've chosen one here that sort of has all the colors of the rainbow in it. This is the function here in this example, cosine pi x over 2 times cosine pi y over 2. That's 0 when x or y equal plus or minus 1. And so you get this nice box around there. But that just happens to be the function I chose, produces this surface plot. This is a great way to represent more complicated surfaces than planes. But it has a very important restriction, is that the surfaces must be so-called single-valued. And what that means is that for every x and y, there is exactly one value of z associated with the surface. All right? So very general. I can put any kind of function I want on the right-hand side of this equation, get lots of different kinds of surfaces, but they can only be single-valued surfaces. And a great example of a surface that's not single-valued and cannot be represented this way is our sphere. X squared plus y squared plus z squared equals 1. All right, that's a very common surface, but it can't be represented in this two-variable function way. You'd have to have one function for the top and one function for the bottom, and that just gets kind of messy. And so quadric representation is better for spheres, but for a lot of other things, two-variable functions are the way to go. And the great thing about them is that you can immediately put them into something like MATLAB and get surface plots, or another kind of plot called a contour plot that we'll talk about on the next page. All right, many planes, not all, but many planes can be thought of as two-variable functions. And so here's a very simple example, right? Going back to last section, take a plane through the point r0 is 1, 2, 3 with normal 1, 2, 1, and write it down as a two-variable function. So we go back, we remember point normal form, and again, I don't like to use formulas or anything like that, so I just remember point normal form. R is the vector x, y, z, r0 is 1, 2, 3, and the normal is 1, 2, 1. So I get x minus 1, y minus 2, z minus 3, dotted with 1, 2, 1. And at the end of the day, I get standard form of a plane. Right? Now, all I have to do to put this in two-variable function form, is solve for z. So I put everything that's not z on the other side of the equal sign, and now that plane is described as a two-variable function. And almost any plane can be represented this way unless the plane is vertical. Then you can't write z equals something because z takes on many different values, infinite number of values in the plane. So a plane can be thought of usually as one kind of two-variable function. This is a more complicated surface than a plane, showing the power of two-variable functions for creating surfaces. Here's another way to think about visualizing surfaces if they're represented by two-variable functions. Okay, so it's the same thing. We've got our function f of xy, and we now say, well, let's look at all the set of points where that's a constant, where c is some constant. So, as a two-variable function, we would say z equals f of x, y, and z. But a level curve is the set of points where that equals one particular value. All right? Only one value of z are we interested in. Where is it equal to that particular value of z that we're here calling c? Okay, so the key idea is that along a level curve, the function has constant value. All right? And so, so if you're thinking of like a surface plot, then z represents height, and so the curve represents positions where the height is the same, constant elevation. Now you may have seen level curves before without quite realizing that they were called level curves on something called topographic map. So a topographic map is simply a set of level curves corresponding to different elevations. So here's a map of the big island of Hawaii, and apparently each curve on this plot represents 1,000-foot gain in elevation. So here's the border with the ocean, that's 0 feet, and then this is 1,000 feet high, 2,000, 3,000, 4,000 feet high, and this is a bunch of level curves corresponding to different values of z, superimposed all on the same map, and that gives you something called a topographic map. More generally, it's called a contour plot in a mathematics class, but on a map, you would call it a topographic map. Here, I've typed something out here to note from past experience. Usually, although our textbook may occasionally throw a contour plot at you that does not have this property, but a well-designed contour plot usually has constant intervals between the curves. So this is a good example, 0, 1,000, 2,000, 3,000, 4,000, etc. If that's true, if it's a well-made contour map, then the closer the lines are, the steeper you are going, right? So this path right here is quite steep compared to this path right here, which takes a long time to cover the same amount of elevation. So that's an important feature to know about contour plots. When the lines are close together, it's very steep. So now, this last page, I want to compare both surface plots and contour plots of the same function, and I want to come back to these particular functions called paraboloids. So there's two goals here. One of the goals is to become familiar with paraboloids because they're important. And the other goal is to be able to look at a contour plot and look at a surface plot and see the connection between them, how they represent the same kinds of shapes. All right, so here's our first paraboloid. It's a downward opening paraboloid, z equals minus x squared minus y squared. So when you look at it from the side, it looks like a parabola, and it is circular. We've got this negative x squared plus y squared here, so it's not surprising that it's sort of circular in nature. And so now imagine looking at constant elevation. So the top of this is evidently 0, is the greatest elevation. And then at some point, it has an elevation of -1. And at some point, it has an elevation of -2. And at some point, it has an elevation of -3. And you can see that as we get farther away from the origin, it gets steeper and steeper. And so these contours might get closer together. Elevation -4, elevation -5, and so on. Here's the same function represented as a contour plot directly from the software program. So here's our -1, -2, -3, -4, and so on. And you can see that they are getting closer and closer together, and that they trace out circles because of this circular nature of this right-hand side. In contrast, here is an upward pointing paraboloid, all right, which looks from any given direction very much like a parabola when you look at it from the side. Positive x squared plus y squared. Again, here the minimum value is 0. Often these are colored so that the minimum value is like a dark color and the maximum value is a light color. So here in this image, we go from blue to red. As we go away, the values are getting larger. The previous image, we went from red to blue. The values were getting smaller as we went away. And again, you've got that 0 point, which is hidden here. And then you've got something with elevation 1, something with elevation 2, elevation 3. And it gets steeper the farther you are from the origin, so the curves get closer together. So these are going uphill at a steeper and steeper rate. Finally, the last kind of paraboloid is this saddle point, this hyperbolic paraboloid or saddle point that we see one more time. And so again, when you view it from the x direction, from the y-axis, so that you see the x direction, it looks like a downward facing paraboloid in x. It looks like an upward facing paraboloid in y. And so we have the downward and the upward, and we get this saddle shape. Now, it's really interesting, last thing in this lecture, to look at the contour plot of a saddle point, because this is the only time you will ever see contours cross. There's some trajectory along this hill that's flat and I cross over the saddle point and it's flat. Similarly over here, it's flat until I cross over the saddle point and disappear on the other side, and I'm not changing elevation. And so you have this cross on the contour plot. And a crossing contours on a contour plot always indicates a saddle point. If we're from this point, if we go in the X direction, we're getting more and more negative, from green to darker colors blue. In the other direction, more and more negative, green to darker colors blue. So this illustrates this case right here. If I go in the Y direction, green to lighter colors red, green to lighter colors red. That's what's happening here. And in the middle, you have this crossing of the contour lines, which you will only ever see, which is uniquely associated with saddle points. In contrast, circles, small circles, indicate either maxima or minima of a function. So a small dark colored circle that's darker than the surrounding area is a local minima. We'll talk about that again in a few lectures. A small circle that is brightly colored compared to its neighbors is a local maximum. And a cross is a saddle point. So that concludes today's lecture.